So in part one of this unit, we looked at just some of the basics. What is a star? What's going on inside? And what are some of the features that are associated with a star and that can affect us here on Earth? In part two here, we're going to start looking at how can we classify these stars so we could describe how they change throughout their existence. And one thing that you should know about in astronomy is that the only way to really study stars and pretty much study anything is to actually look at the light that's coming off of them. All right, it's nice to go to the moon and collect samples. It's nice to go to other planets with little rovers or send satellites around things. But really, the only way that we study and learn in astronomy is by looking at the light. All right, 99% of all the light information we have about the universe comes from that light that an object emits, reflects, or absorbs. So, what do you notice about the two stars in this picture here? Obviously, the difference here is that one's blue, one's yellow. All right, different colors. So what does that tell an astronomer? All right, that's what you should have started to look at in the spectral classification activity. If you have not done this yet, you should do this first. So there'll be a hot link. Click here, go do it, then come back and finish this podcast. If you've already done it, let's move on. All right, so those different colors are actually telling us what the spectral classification is of that star. What's the spectral type? Is it an O star, B star, A, F, G, K, M? All right, and all of that tell us or can be given by looking at the star's surface color, all right, or surface temperature. And why is it a certain color? For example, why is ours yellow? Or why are there red stars or blue stars? All right, that all deals with the surface temperature of the star. Not the interior temperature, but the surface temperature. And what you would think is that, most people at least, think that blue is a cool color, so that's the coldest stars. And red, red hot, those are the really hot stars. In fact, it's the complete opposite when you're dealing with the energies associated with different temperatures or colors. All right. If you know the guy Roy G. Biv, that goes through the colors of a rainbow: red, orange, yellow, green, blue, indigo, and violet. And it goes in order of lowest energy, so therefore cooler, all the way to the highest. All right, the blues, indigos, and violets. Now, what you should see here is that the coolest temperatures are down here at the reds, 3,000 degrees on the surface. That does not mean the interiors of the stars that are red are the coolest. It might be the complete opposite. This is just the surface. On the far other end, the really hot surface temperatures, 50,000 degrees Kelvin or more, all right, are the blues. Now, here's something that should be popping up. All right, you can see we have red, orange, yellow, green, blue, indigo, and violets in a rainbow. Well, where are the greens? All right, the greens seem to be replaced by white. And that's the assignment that follows this. Why are there no green stars? Do a little research, find out. Now, our sun is yellow, so therefore it must be a G-class star, and technically it's a G5. You can take these and subdivide them up into 10 different parts, but we're not really going to go into that. So great, we know what spectral classification our star is, but all right, other information that we can get from looking at a star's light. All right, most of our sun is made out of hydrogen and helium, but we didn't go to the sun and pick this stuff out. We didn't go to other stars and take a scoop of what they're made out of and then analyze it. We look at the light that a star is giving off. All right, and the light that it gives off could be put into one of three spectra. All right, it could be a continuous spectrum, it could be an emission spectrum, or an absorption spectrum, depending on how it's being produced, how that light gets to us. All right, so let's first look off at the continuous spectrum, and as you can see, it's continuous. It goes from one color into the next and just bleeds into the next and so on, so there are no breaks. And this could be caused by a glowing solid. Okay, you ever put a poker for the fire. If you put it in there for a long time and pull it out, it'll be glowing. All right. If you were to look at the spectrum, all right, of that, it would be glowing in all the colors, red or orange at the most, though, most intense. Or you could have a liquid, all right, that's heated up and glowing, or just a really condensed gas like our sun. All right. Now, obviously, where have you seen this before? It is a rainbow. All right. When you look at a rainbow, what you're seeing there is light from the sun going through a prism. In this case, the rainbow is caused when light goes into a rain droplet, which kind of acts like a prism, and then splits it into the different types of light that are that make it up. So when you look at the sun's spectrum and a rainbow, you see a continuous spectrum for the most part. We'll come back to this a little bit later. All right, an emission spectrum. An emission spectrum looks different from a continuous because it doesn't have all the colors of the rainbow. It just has bright lines. All right. Now, why does it have bright lines in certain spots? That gets into the structure of the atom. We don't need to get into that here. But it's caused by a low density excited gas. All right, kind of like a neon sign. All right, if you ever see a neon sign, or if you have fluorescent light bulbs, all right, there is a little bit of gas in there. It's low density, and when you put a voltage across it, it causes the atoms inside to be excited, and that produces the light. So if we look at, say, hydrogen, what we would see if we allowed that light to pass through a prism that split it into the different colors that made it up, you would see a red line, a blue line, a light blue, and a darker blue line. Helium has a slightly different spectrum. All right, it does have a red, but it also has a yellow. It's got a couple light blues, got some other blues. And then an actual neon sign, that glow orange. All right, if you were to look at that neon sign through a spectrum, a spectrograph, or some diffraction gradient lenses, you would see something more like this. A lot of different little lines. What you should see here is that they're all different. And that different aspect is key. Think of a spectrum, an emission spectrum that is, as a fingerprint. Everyone has a different fingerprint. All right. And if you can identify a fingerprint of a person, all right, you know who's been someplace. If you can identify the spectrum in a star, you know what that star is made out of. All right, so that's kind of how it works. Now, beyond just what it's chemically made out of, you can get all kinds of really good information, and it's really important that you write all these down, all right, and study them. All right, you can get information about the star's temperature. You can get information about its rotational speed. You can see whether it's moving towards us or away from us. You can see if that's how dense that star is, and even information about its magnetic field. So this is more important if you're just looking at how much data you can get than looking at a really nice Hubble Space Telescope picture. All right. The spectrum gives us all kinds of goodies in detail. All right, absorption spectrum. All right, kind of looks like continuous, but it's got dark lines in it. And those dark lines are the complete opposites of the emission spectrum. All right, and these are caused when you shine light through a low density cool gas. All right, it kind of acts like a filter. If you ever worn lenses that filter out certain kinds of light, all right, that's basically what an absorption spectrum, or how an absorption spectrum is produced. All right. So for example, let me show you what one looks like. Here's the emission spectrum of hydrogen, and here's the opposite, the absorption spectrum. All right, complete opposite. And really, if we go back to looking at our sun, astronomers don't really see a nice rainbow. All right. If we were to stretch this spectrum out, we would start to see that there are actually lines in it. And the lines come from when you have that continuous spectrum going through the cooler parts of its atmosphere. The cooler part, instead of giving off light, actually absorbs different wavelengths. And depending on what's made or what is floating around in the sun's atmosphere, gives us different absorption lines. And in fact, if we were really looking close, this is what we would see. We would see a lot of absorption lines, which means there are a lot of different chemicals floating around in here. And what scientists can do, all right, is actually pick out the different spectrum that are found in here and identify what's in our atmosphere. All right. So, for example, here's an unknown gas. Let's say we're looking at a cloud of gas and we see this absorption spectrum. Well, we can take known emission lines of different gases and compare them to those spectrum lines. And we can see that, for example, carbon, no way carbon's in here because you'd have to have a dark line for every bright line you have up here. And there's just none in here. Boron looks close. You got this dark line here, but there are no orange, and the yellow's out of place. When we take a look at the helium, all right, things line up really well, and then also the hydrogen. All the lines are accounted for. So therefore, we can say that hydrogen and helium are the main components of this gas. All right, so that was a quick rundown of the 3 types of spectrum, what they're used for, and spectral classification.